time of computation for overland is 7 minutes. 7 minutes. For the channel time, you use the Magnus equation, and for the pipe time, okay, you will use the Darcy-Weisbacher. Okay, this one you will use the Darcy-Weisbacher equations. Okay. Okay, now actually we have no exercise as I mentioned yesterday. So I may give you 10 minutes. Okay, maybe 10 minutes. Okay, 10. See whether you can complete the questions. Okay. This question actually is 2017 exam question 1. Have you downloaded the exam paper 2017 from the Canvas? Let me see. Great. That's great. Let's have a look at this question first. Okay. So this is the questions of the 2017. Okay, 2017. Okay. So for this question, actually, you need to find the flow. Sorry. So you need to find the flow into pit A and pit B. Actually, you can see there are two sub-catchments. One is the parkland, so one is the paved area. So you can see the parkland, so the runoff to the pit A. So for the paved area, so the runoff means the surface runoff to the pit B on pit B. So, and also you can see there are two paths, path AB and path BC. So actually the question, you need to determine the flow into pit A and the flow in the path BC, flow in path BC. From 20-year ARI storm, 20-year ARI storm. Now from 20-year ARI storm, actually the use the intensity, frequency, duration table for Hong Kong is attached. Okay, so that means you need to use the table attached the table. Where attached table? Not here. I think this one. Okay, you can use this table. Okay, or you can use this equation. Use this equation to calculate. Okay. So and also the more information means the 100% pervious for the parkland and the paved area in direction of the arrow leading to pit A and the pit B, and the slope is 2%. Slope is 2%. Okay, and let me see. The time of completion of the paved area is 5 minutes, and also the parkland is 25 minutes. So actually, it is easier now because the time of completion given here. Okay, the runoff coefficient for the paved area is 0.8, and for the parkland is 0.2. Okay, it's the C. So the surface slope in the direction of ABC is 1%. So that means the path. Slope of the path is 1%. So the average path size ranges from 225 mm and up to 1,200 mm. So increase in step 75 mm. Okay. So above 1,200 mm, so the step size normally we take 150 mm up to 2,500 mm. And also the equations for the formula, the rational method, the formula is given. Okay, so here, okay, you need to pay attention. It's about the unit of the area. Okay, of the area. So the area of in this question is square kilometer. So that means you can see the factor is 0.278. But in some questions, they may use hectare or other units. You be careful here. And also for this is the Darcy-Weisbacher equation. Okay, So the first factor given 0.015. Okay. Okay, now actually you have downloaded that the paper. Actually you have this exam paper hand. Okay, so try that. Okay, I give you 10 minutes. Okay, so and then I will show the solutions of this question. Is that clear? Okay. Time the minutes. Is that clear? Hello. Okay. 10 minutes. Okay, 10 minutes. Attempt these questions. Okay, so there are 10 minutes. So anyone finish this question, or do you need a few more minutes? Hello. Okay, good. 5 more minutes. Okay. Okay, 5 more minutes. Okay, good. Anyone finish these questions? So anyone finish the question, please let me know. Okay, so so for this question, I think it's you need to do what you need to do is to find out the intensity, the rainfall intensity for each subcatchment for the parkland and for the pivot area. Um, with a given time of concentration, with a given time of concentration. So then you can calculate the peak flow, okay, the flow to the peak A and peak B, okay. And the next you need to determine the path, okay, the flow in the path, and also determine the size of the path. So starting from 225 mm, okay. Um, so um, so anyone finish that? Let me know, please. um, so already 20 minutes. Sorry. Okay. So so anyone have finished that? Hello. Uh, the pipe length of AB. The pipe length of AB is 40. Yeah, half 40 meter. Yeah. Okay, great. I see one student finished the questions. Used the 25 minutes. 25 minutes. So anyway, so this question is actually is about to use the rational method to estimate the peak flow to the pit A and pit B, and also to estimate the flow in the path BC. But actually, to get the flow in the PEP BC, you need to get the flow in the PEP AB first. Okay, so first I will show you the solutions of these questions. Okay. Okay. Now for this question, actually, there are only two subcatchment, the parkland and the paved areas. So that means for the let me open the questions. So for the parkland, we can see that the area is 100 meters times 60 meters. Okay. For the paved areas, the area is 80 meter times 60 meter. Okay. So firstly, to get the intensity, okay, to get intensity from the table, okay, from table, or use the equation. Now for the parkland, the concentration times 25 minutes. 25 minutes. So from the table, you can find out the ARI. So the ARI 20 years. 20 years. So you can find out. So you can find out the intensity 150. 150. So I think I need to show you this one, right? Because this I think is very important. Just to share this one. Okay. Now from page 2, okay, from page 2, the questions for the 2017 exam paper questions, you can find out the ADF table, So for the parkland, the time concentration is 25 minutes, and also the ARI is 20 years, 20 years. So you can easily find out the intensity, the rainfall intensity 150. So for the paved area, so we can see that the time of the concentration paved area is 5 minutes. 5 minutes. So 5 minutes is here. 5 minutes here. So you can see the intensity is 245. 245. Okay, 245. Now, after you get the intensity from the table, from the ADF table, so you can use the rational method to calculate the peak flow to the pit A and the pit B, pit A and pit B. Okay, so for example, for the pit A, so you can see the this is for pit A. Okay, so this is for pit A. Pit A. So the using the rational method. Okay, so the factor the C, the runoff coefficient is 0.2 and times 150. So this is the 150 is the intensity, rainfall intensity, and times the area. Okay, and also over the 1000 times 60 times 60. Actually, this is conversion of the unit. So finally, you can see the peak flow to the pit A 0.075 cubic meter per second. Do you have the same answer? Okay, now next is the pit B. Similarly, pit B, so the area is here, this runoff coefficient 0.8, and the time of concentration 5 minutes, you can get the intensity 245, okay, millimeter per hour. So use the rational method, so you can get the pit B. So you can get the pit B, the peak flow to the pit B 0.261. So the next, you need to determine the size of the PEPs, the size of the PEPs, okay? So we need to use the Does whisper her equations. Does whisper to get the velocity, the velocity of the flow in the PEP AB, because we need to determine the time, the total time. So we can see that the slope of the PEP is 1%, and also the frequency factor is given 0.015, and also the PEP size we start from 225 millimeter. So we can get the velocity 1.71, 1.71. Okay, 1.71. So, but you need to check in this question. You need to check whether the capacity of the pipe is suitable. The capacity can be used. I mean, this pipe size can be used for the pit A, for the flow in the pit A, in the pipe AB. Okay, because the pipe AB flow, the flow in the pipe AB actually is the flow into the pit A, into the pit A. So after getting the capacity, you can see the capacity of the pipe AB is 0.068, 0.068. No, here. This is about the pipe AB. So actually, you can see that the capacity less than the 0.0775, because we calculated the peak flow to pit A is 0.075. So you can see the pipe capacity is less than 0.075. So that means this pipe size is not suitable for the pipe AB. For the pipe AB. So next step, try another pipe size with diameter 300 mm. Okay, with 300 mm. Similarly, you can get velocity. You can get the flow, the capacity. Okay, the capacity of the pipe 0.14 cubic meter per second. So now it's okay. Okay, now it's okay. You can see that. So that means the pipe size should be for the pipe AB should be 300 mm. Now with the velocity, so with the velocity, you can get the time in pipe AB. Means 40 meter. 40 meter. So the time is 40 meter. 40 meter over 1.98, around 20 seconds. So we assume that is 0.33 minutes. 0.33 minutes. And also you can approximate that to 1 minute. Okay, for example, here you can approximate that to 1 minute. 1 minute. So finally, we get the time of the compression 26 minutes, because the pipe line, the time of compression in the pipe line is 25 minutes. So in the pipe we assume it's 1 minute. Pipe we assume the 1 minute. So we get intensity. Okay, so we can get the intensity from the table or from equation. Okay, this one here you can get it from the equation, because there's no 25 minutes intensity in the table, so you can use the equation. So next we need to calculate the pipe, the flow in the pipe BC. The flow in the pipe BC. Okay, so with intensity and also with the actually the pipe BC, as we know that there are two subcatchment contribute to the pipe BC. Means the pipe line and also the pipe area. The both contribute to the pipe BC. Both contribute to the pipe BC. Okay, so here you can see that we need to use the pipe line and also the pipe area. Okay, use the same intensity. So finally, we can get the flow in the pipe. We can get the flow in the pipe BC. So 0.23 cubic meter per second. Okay, cubic meter per second. Okay, so actually this question is actually asking to estimate the let me see. Yeah, the flow in PEP BC. The flow in PEP BC. Actually, not ask you to determine the PEP size of BC. Okay, so if you are asked to determine the PEP size of BC, so you can see that the diameter 300. So you can see the diameter. If the diameter 300, so the capacity is 0.14. Is 0.14. So actually, it is not suitable for the PEP BC because the PEP BC is 0.23. So that means you need to try another PEP size, maybe 375 or 450 millimeter, to see whether the capacity is suitable or not. Okay, so this is the questions in the exam paper 2017. So any questions you have? You mean which intensity value? 26 minutes or? Now in this question, actually they use the IDF table in the exam paper. You know, use the IDF table in the exam paper. Okay, because this is 2017. This is not updated version of from the manual. Okay, I think you use the manual 2018, right? Am I right? Okay, it's fine, but it's fine because this is 2017 exam paper, so they use the old version of the stormwater measurement manual. Okay, so in the old version, so you can see that the ABC different. Okay, so the main purpose actually of this exercise actually is to let you to enhance your understanding of how to use the rational method. Okay, so but actually if we in the final assessment, so the equations and also the tables we provided with updated version of the stormwater measurement manual. You know, okay. So this is question. Any questions still have? Okay, great. Yeah. Now, if you have no further questions, we'll move on to the next topic, I think. Okay. Great. Let me change the file. Okay, so that we introduced the rational method. So next we have the, let me see, week 4. Week 4. Okay. So week 4 actually is it's an application. It's an applications of the rational of the urban drainage system design. So let's have a look at the pipe system design. Okay, pipe system design. So firstly, we here I think we are assumptions. Okay, assumptions of the pipe design of the urban drainage system design. Okay, so firstly, there's steady flow in each pipe or the link. Okay, means it's a steady continuous flow in the pipes. So secondly, the flow, the peak flow rate are from the hydrological model. Okay, here when we use the rational method. Okay, so that means the peak flow rate is from the rational model. Okay, rational method model. Okay, and also HGL means hydraulical grid line runs along above upward of the pipe. So pipe is flowing full but not under pressure. So this one is quite important. Okay. So that means the HGL. So the hydraulic grid line. So hydraulic grid line is called cones. So called cones the upward of the pipe. Okay, upward. And also pipe is flowing full. Okay, the pipe is flowing full, but not on pressure. Okay. Be careful here. Okay, not on pressure. Okay, not on the pressure, because they'll be different. Okay, they're different. So if this is under pressure, so if it's under pressure, I will show you like next slides. I think if under pressure, so the HGL will be different. The HGL will be different. And also the pipe size determined by the DW formula. DW formula. What is DW formula? The Darcy-Weisbach formula. Okay. Darcy-Weisbach formula. So mine is this one. This one. So energy in the PEP in design of the PEP system, actually we also need to know. We also need to calculate the energy loss in the pitch. Okay. So because the pitch generates the turbulence, so that causes the energy loss and a drop in the HGL. I will show that later. So normally we use this one to calculate the drop energy loss. The energy loss in the pit. So K is a coefficient. V is the velocity of the flow, and also over 2G. And limiting the slopes, velocities, and diameters. Okay. And also, as I mentioned, that to prevent the sediment and also to prevent the erosions. So the velocity actually minimum 0.6 meter per second, and the maximum 3 to 8 meters per second are used. And also the diameter actually minimum 150. So using the Darcy-Weisbach formula, we is used to trial is used for trial pipe diameter to find the slope. Okay, needed to convey the flow rate already computed. But actually, you need to try. You may have several trials to determine the pipe size. As I just showed an example. Okay, maybe you start from 150. Maybe the size is not suitable, and you try another one, 225, or try another one, 300. Okay. So actually, the I just back to the Darcy-Weisbach equation. Actually, HF normally is about the head loss. The head loss of the flow in the pipe. Okay. So that's why we use the here assumptions. It means the HGL runs along upward of the pipe. So the pipe is falling full but not on pressure. Okay. So normally the HGL is the same. It's the same. That means runs along the surface of the water. Runs the surface of the water in the pipes if there's no pressure. But if the pipes under pressure, the HGL will be different. The HGL will be higher. So based on the assumption, actually the HF means the head loss actually over L actually is the slope. Means the slope of the pipe. Now we can use this one to back to this one about the energy loss. I just provide more information. So the pit generate turbulence. Why they have the energy loss in the pits? Because when the water enter into the pit, so the pit generates the turbulence. Okay, the turbulence. So the turbulence actually causes the energy loss. Okay, turbulence the energy loss and a drop in the hydraulic grid line. So this loss, normally we use the coefficient key times the velocity head in the pit outlet pipe. Actually, there are a number of design charts available. Design charts, okay, available to find out the key. To find out the key. So actually, the energy loss actually can be avoided. Okay, by design and construction. Okay, just give a simple examples. For example, make sure that the water coming from the upstream pipe is directed towards the entrance of the outlet pipe. So that means there's no the bendings of the pipes. Okay. Now next one, this slide showing the actually this slide showing the pipe designs system, and also the terms we used. Another terms we used in the pipe design. Terms used to be used in the pipe design. So actually, for the hydraulic, actually this figure also help us to understand the some kind of the terms such as energy loss, friction loss, pressure change, and what is the HGL, etc. So let's see. Firstly, the surface elevation. The surface elevation. So the surface elevation here. Okay, the surface elevation. So the surface elevation actually normally is the gutter level at the pit lid. The gutter level at the pit inlet. And also another one is the free bore. Free bore means what? Means the from the surface level, from the surface elevation to the water level. Okay, it's called the free bore. I mean, from the pit water level to the surface elevation. We call it free bore. Actually, this one is normally we use the 0.2 meter. 0.2 meter. And also, you need to understand the HGL level. So the HGL means the hydraulic grid line. And also the another one is about the TL. TL means the total energy line. Okay, total energy line. So this the hydraulic and total energy grid line under concept actually are from the Bernoulli equation. Bernoulli equation. So I'm not sure whether you have learned the Bernoulli equation. So the Bernoulli equations actually means in a steady flow. Okay. So the sum of pressure energy, kinetic energy, and the potential energy remains constant, means remains unchanged. Three types energy, okay, in a steady flow: pressure energy, kinetic energy, and the potential energy. I mean, three types energy. The sum, means the sum of the three types energy remains constant at any section. If you know energy is added or taken out. So based on the Bernoulli equation, so we know that the pressure energy plus the kinetic energy plus the potential energy actually is equal to a constant. So actually, in the pipe flow, actually the energy changes, and also the energy losses. For example, to a higher elevation to a lower elevations, so we can see the potential energy. Part of the potential energy changes to what? To the kinetic energy. If there are no change of the pressure. Okay. So of course there are lost. They are energy lost. So they are energy lost. Okay, so they are energy lost from upstream to the downstream pipes. So here you can see the first one is about the peak pressure change. Peak pressure change. Peak pressure change. So actually, this chart actually shows the pipe actually is under pressure. Okay, it's under pressure. Okay. So means the water in the pipe is under pressure. The water in the pipe is under pressure. So that means if the water in the pipe on pressure, so that means in the pit. Okay, so there'll be a pit pressure change. Because the in the pit the pressure is the atmospheric pressure. Okay, it's at atmospheric pressures. So that means the pressure change. So there'll be a loss. There'll be a change of the pressure change. So that means the grid line. You can see the hydraulic grid line drop due to the pressure loss, the pressure loss, the pressure energy loss, So you can see the difference. Of the total energy line and also the hydraulic grid line. And also another loss you need to know is the friction loss. Because the pipe, okay, the surface of the pipe is not smoothly without any friction. Not any type of the pipe will have a friction loss. Okay, friction loss. Okay, so we use this one to calculate the friction loss of the pipe. And next is about the pit energy loss. As I mentioned, pit energy loss because of turbulence at the pit. So actually, there's a pit loss in the at the pit. Okay, because there's a pit energy loss at the pit. Okay. So for the pit pressure change, actually, because the manholes in the pits are near always larger than the pipes, and also the expansion of the pipe flows, and also the mixing of the pipe and the surface inflows and the effects of downstream water levels create complex flow conditions missed at the pit. And also this will result in the energy loss and also increase the water level and sometimes causing the overflows. Okay, so pit pressure change because the pit pressure change. Now the pit energy loss, though, because the significant energy loss may occur at the pit and the pipe junctions, especially if the pipes are on pressure. So as we know that the capacity, so the capacity of the pressurized pipe is greater than the open channel flow. Okay, means this if the pipe is under pressure, so that means the capacity is higher. So the capacity of the pipe is higher than the open channel. So the energy loss is higher. And also the another one is the head loss. The head loss actually is about the kinetic energy loss due to the friction in the pipe. Okay. Sorry, the head loss is due to the turbulence caused by the pit configuration. Okay, and also the friction loss is because the friction of the pipe. Okay. And also you need to know the pit drop. There's a pit drop. Okay, pit drop. So the pit drop. The pit drop actually is used normally is usually 30 millimeter. So actually, this pit drop actually is used to prevent any sediment in the pit. To prevent any sediment in the pit. And also remember the cover depth. Okay, the top I already mentioned that the cover depth actually is from the surface to the top of the pad. The top of the pad is the 900 millimeter for the carriage weight, and for the foot weight, the minimum is 450 millimeter. 450 millimeter. So the normal procedures of the calculations actually is from the upper reaches of the system to the receiving water. Means from the upstream pipes to the downstream pipes. Okay, so if the outlet pipe is too low or too high, so we need to back trace up the system and also carry out the alterations. And also, I think in the assignment one, actually you actually is about how to design the pipe systems. Okay, design the pipe systems, and also you need to use the spreadsheet, listening spreadsheet to calculate. So actually, this is example. In the let me see examples actually in the lecture, I think. Okay, in the lecture to how to design the pipe flows. Okay, determine the pipe flows, pipe slopes for pipe system design. Okay, so I'm not going to here to go details of these slides, I think. Okay, so if you have any questions, so you may ask that later. Okay, ask that later. Okay. Okay, now I have now I see I have a poll here. What the poll questions? Okay, here's one. Let me cover. Oh, I just mentioned these questions. I just talked about these questions, but I'm not sure whether you click on that. Okay, it's a poll questions. Okay, now you can complete the questions, and also we have a break of 10 minutes. Okay, so and I will leave the poll here so you can complete the poll questions and also have a break. Okay. Looking back around 10:50. Okay, have a break. Okay, back at 10:50, and also at the same time you can finish the poll. Finish the poll first. Okay. Great. Okay. So after a short break, so we will continue of this morning's workshop. I just give you a pose of the questions of the minimum cover from the surface of the carriageway to the top of the pipeline. So the correct answer is 900 millimeter, 900 millimeter. Okay. And also for the pipe system design. So here examples, and also this example has, you can find this example at the details, the calculation details in the e-test book, So but if you have any further questions, you can send me email. I will not go details of this example here. Now here's just a summary of the pipe design. Pipe system design. So actually we use the hydraulic model. For the small catchment, we use the rational method. And also we need to determine and also the pipe size, and also we need to know the limitations. Okay. So inspect the pipe friction losses. So to find out if the pipe is too small, okay, and also the larger pipe is required. I mean to use the Darcy-Weisbacher. Okay, you remember? The Darcy-Weisbacher equations to find out the velocity, to find out the velocity in the pipe, okay, and also to with the velocity you can get the capacity of the pipe to check whether the capacity is larger than the peak flow in the pipe, okay. Another design process proceeds from upstream to the outlet, okay, means from upstream pipe to the outlet, and also the checking purposes, the process, actually the checking process actually is reversed as illustrated. Means you need to check from the outlet back to the upstream pipes. Okay. And also the calculations can be implemented a spreadsheet, and you can. But actually, you are asked to. But actually, you are need to. Actually, you need to. Understand, okay, understand the process, and also in the assignment, actually the template of the spreadsheet provided, okay. So, but actually you need to understand the process, okay. You need to determine the values of each in the spreadsheet, okay. In week 5, actually, it's about the professional issues. Actually, actually, this topic actually in this topic actually you can see there are a number of examples. I think, okay, a number of examples of the of designs of the water sensitive urban designs. Okay, so firstly, in this topic, actually introduce the evolutions of the drainage design. Um, so, for example, how to prevent the flood, okay, how to improve the stormwater quality, and our water conservation, and also talk about the climate change. Actually, yesterday afternoon, at the beginning, I also talked about the climate change. Now it's becoming more and more important issues for the for the world. Okay, because you can see that now in recent years there are more and more extreme weather events. Okay, and also the WSUD, the water sensitive urban design. Actually, this concept is used in Australia. Is used in Australia. So the stormwater actually is the rainwater actually on the road, the roofs, and from other properties or infrastructures often contains the chemicals and pollutants. So the water sensitive urban design actually is used to plan and design the urban areas, okay, to make sure the to make use of stormwater. I mean, okay, to make use of how to make use of the stormwater, and also reduce the harm before it releasing to the river and the creeks. Means before it, how can we remove the pollutants? Okay, how can we remove the pollutants before it released to the rivers and the creeks and the other water receiving bodies? And also in this design, in the water-sensitive urban design, actually in this topic, I think there are many real cases are introduced, such as the wetland, manor rock swales, the rain garden, etc. Okay. And also there are two construction techniques introduced. One is the gravel trenches, and another one is infiltration zones. Okay, so the gravel trench is also called infiltration trench. Actually, it's used to manage the stormwater runoff to prevent flooding and the downstream erosions, improve water quality. Okay. Actually, it is a shallow trench. It's a shallow trench filled with gravel and crushed stones. Okay, so it is used. It is designed to infiltrate the stormwater through the permeable soil into the ground. And also the infiltration zones or basins are shallow. Okay, are shallow impounded areas. Okay, are shallow impounded areas. So actually, they are designed to temporarily store and infiltrate stormwater runoff. Okay, so that means the infiltration zones is used to temporarily store the stormwater and also infiltrate the stormwater runoff. Infiltration means to working as a filter, means what as a filter to remove the pollutants in the stormwater. Okay. And also there'll be some kind of real cases of rain gardens to introduce in the I think in the lecture. And also another one is for the resident education. Okay. So normally there'll be send out. So the government department maybe send out the 3 letters to the local residents. The initial letter actually to inform the upcoming works with environmental considerations. So the second letter, so we will request the help from the residents to get their opinions and to explain what will happen on site, and also get feedback from the local residents. So the third letter actually will invite the residents to meet the on site to get further feedbacks. So the key message for the education is to encourage to attend the training sessions, to encourage the staff, So and also to encourage the practitioners, the developers, the consultants to use the water-sensitive urban design. Okay, and also to identify any potential applications of the trial project. And also the last also introduced the rain garden and constructions with the good examples. Okay, with the examples. So this is a professional issues actually to let you know more about the water-sensitive urban design, and also there are cases in Australia. Now let's move to the week 6. Week 6 actually is about the detention basin design. So detention basin design. So design philosophy. So let's look at the design philosophy. So this actually there are two figures shown here. The red one is about the storage basin, inflow and outflow. So the storage basin. So what we need to know is to get the two hydrograph about this storage basin. So one is the inflow hydrograph, another one is the outflow hydrograph. Okay, so how can we get these two hydrograph? Okay. So use storage basin actually is to alter the inflow hydrograph, so the peak flow in the outflow hydrograph is reduced and delayed. So what that mean? So you can compare these two curves. One is the inflow, the blue one is the red one, the outflow hydrograph. So you can see you can compare these two hydrographs. So you can see the outflow, the peak is lower than the inflow, and also the time is also delayed. Okay, the time means that the peak flow time is also delayed. Okay, so this is the one philosophy. So another one is the peak post development runoff rate do not exceed the peak pre-developed runoff rates for a given design rainfall. So that means the red one, for the red one, the peak flow is here. The peak flow is here. Okay, the peak flow, red one for the means for the outlet, for the outflow. So for outflow hydrograph, you can see the peak is here. So the peak flow rate, so do not exceed the peak pre-development. That means the natural catchment, runoff rate. Normally, the natural or the pre-development runoff rate is very low because what? Because the most rainfall becomes the infiltration, to the soil, becomes infiltration and becomes interflow waters to the absorbed, because most of the rainfall absorbed by soil, becomes the interflows or groundwater. So, but for the post development, so the most rainfall becomes the surface runoff. So that's the difference. That's the difference. Okay. So why we need the storage basin? Where we need a storage or detention basin, we need to make sure the peak flow, do not exceed the pre-development runoff rate. So we can see that as a stormwater detention basin actually is normally to use to collect and temporarily store the stormwater. Okay, and also releasing the water to the downstream slowly, and reduce the risks of flooding. Okay, so for the design philosophy, is actually just to mention that use the storage to alter the inflow hydrograph. Okay, so the peak flow in outlet is reduced and delayed. So this is the design philosophy. So design criteria for the quantity control. So the second is the design criteria for the stormwater quality control. So the peak post development runoff rates should not exceed the pre-development runoff area. So, but another question is here. Okay, how do we determine the size of the storage basin or the detention basin? Okay. So actually, the size of the detention basin can be determined by using the flow hydrographs, means these two hydrographs, inflow and outflow. So actually, this two hydrographs show how much water is flowing in and out of an area over time. So the maximum volume of the temporary storage is used to determine the size of detention basin. So which is introduced later. So the detention basin here, actually normally the volume added to the storage is this part. You see that? Okay. The volume added to the storage. Is this one. It is one. So that means the size determined by using this volume. Volume added to the storage. So we need to determine the area. So we need to know the area. So the area is what? So the area. So this area is what? This area is the. I use another color. So this area. So this area is the volume. So this volume is this area actually is used to determine the detention basin size. So the detention basin actually is used to hold a certain volume of water. So actually, typically, they are designed to hold the water for 24 hours. Typically, okay, for a 24-hour rainfall event. So other factors also affect the design and include the rain intensity, the area of catchment, etc. Okay. So you need to be careful to understand the meaning of these two graphs, of these two hydrographs. Okay, two hydrographs. So one is inflow, one is outflow. Okay. So detention basin design. So how can we control the outflow hydrograph? So actually the two ways we can control the outflow hydrograph. So one is the basin geometry. Geometry means the geometry of the basin, means the stage, the height of water, and the storage. That means the volume of water relation. So for example, a large detention basin can hold more water and also can reduce the peak flow. Outlet, and also another one is the outlet hydraulics, means the stage and the discharge relationship of the basin. Means the stage means the height of water in the basin, and then also the discharging from the outlet structure relationship. So there are two methods used to control the outflow hydrograph. Okay, basin geometry and outlet hydraulics. So the basin, how design the basin, the detention basins? Normally the basin length to width ratio should be between 2/1 and 3/1. Means the length and width ratio means 2/1 or between 2/1 and 3/1. So the flood flow can expand and diffuse into the water body to enhance the sediment process. So how about the slope? The set slope actually should be no steeper than 4h/1v. Okay, h means high, means it means the height of the detention basin. Sorry, horizontal. H means horizontal. The horizontal of the detention basin 1/1v. 1v means 1 is the vertical. Vertical means the depth of the detention basin. Okay, means 4 horizontal and over 1 vertical. So it means no steeper than this one. Okay, so this is the set slope requirement for the detention basin. Okay. So the geometry of the basin should be designed for multiple flood event. Means, for example, for the minor event and also for the major event. Okay, for the lower storage volume in the basin entry is normally used for a minor storm water event. Okay, for example, it's for 2 years or 10 years. That's it. And also the volumetry for a major event. Okay, for a major event. Normally the wheel crest, normally should provide it to accommodate a major stormwater event. For example, here you can see there are two outlet. There are two outlet for the low storage. For the low storage, normally we use the low flow outlet. Okay, low flow outlet means. For example, if the water, if the storm water level is here, so normally you can see that we use this outlet. We use the low flow outlet to release the water to the downstream areas. Okay, but if the water level is higher than the weir crest, means for example, if the water level is here, so we can see that there will be two outflow outlet. One is the low flow outlet, another one is high flow spillway. Okay, so that means the more water can be released to the downstream in a major event, for example, 50 years major rainstorm event. Okay, next the steps in the analysis means how can we get the firstly we need to get the inflow. Okay, how we get the inflow hydrograph. Okay, so here are the steps. Totally you can see there are 6 steps to get the inflow hydrograph. I think so. To calculate the peak discharge, okay, into the basin on the pre-development period. So rational method used. Now step 2, calculate the input hydrograph to the basin for the given development of area. Means post-development, means the hydrograph. So how to calculate the hydrograph? So we use the time area analysis. Okay, time area analysis. Okay. So next, we need to know the relation between the height of water in the basin and the volume of water in the basin, based on the geometry of the detention basin. So then the relationship between the height of water level in the basin and the discharge from the outlet of the basin, to get that, based on the hydraulic models, So the relationship between the input and outflow hydrographs depends on the basin geometry and the basin outlet to get outflow hydrograph from the basin using routing principles. Okay, so these steps actually not include the inflow hydrograph, but also about outflow. Means how can we get the two hydrographs, inflow and outflow. Now step 6, change the basin design, outlet design until the peak outflow from the basin is less or equal to the peak discharge from the pre-development period. Means we need to have some kind of adjustment later, because we need to meet the criteria. The criteria is that the peak outflow from basins should be less than the peak discharge on the pre-development period. So that's the principle. But this is the final design principle. Okay, so that means we will need to use the time area analysis. Okay, time area method to determine the inflow hydrograph. Okay, determine the inflow hydrograph, and also we use the routing. Okay, we use the hydraulic routings to determine what? To determine the outflow hydrograph. So this is quite important. So we need to get these two. So for detention-based design, we need to know these two hydrographs. So quite important. Okay, so for the step 1, actually pre-development peak discharge, we use the rational method here. Okay, so apply the rational method to the whole catchment to calculate the peak pre-development flood level. So here for the time of concentration, actually in the previous catchment, for the rural catchments, actually we use this. So we can use this formula. Okay, so we can use this simple one. Okay, we can use this simple one to estimate the time of concentration. So this is quite a simple one. So means if we know the area, okay, we can use this simple one to estimate the time of concentration of the pre-developed area, time of concentration of pre-developed area. Now the here you can see the C1, as we mentioned, is the runoff coefficient. Okay, runoff coefficient. Runoff coefficient actually is a dimensionless factor. As I mentioned, we also have another coefficient called Manning's coefficient. Manning's coefficient. Manning's coefficient actually is another. It's not dimensionless. It's not dimensionless. So here, runoff coefficient actually is used to convert the rainfall amount to runoff. Means the percentage of the rainfall convert to the surface runoff. Convert to the surface runoff. Actually, it depends on the many factors such as land surface, slope, degree of saturation, the rainfall intensity, and also the temporary storage of the catchment, etc. Okay. So it is also affected by the water table, soil compaction, vegetation, depression, storage, many factors. But as I mentioned, that the runoff coefficient is lower for the natural catchment because the soil absorbs most part of the rainfall. Okay, so the runoff coefficient is lower for the natural catchment, but for the post-development area, such as the road, the roof, and also other infrastructures, normally this runoff coefficient is higher. For example, could be 0.7, 0.8. Okay, So that means most the runoff convert to the surface runoff. Most the runoff, so rainfall, sorry, not runoff. Most the rainfall becomes the surface runoff because there's no, because the surface is the surfaces are impervious. Okay, and also without the vegetation, So most rainfall becomes the surface runoff. Now, step 2, we need to use to get the input head graph. So normally the time area method is used to determine the input head graph. So here you can see the figure. We can see the this method actually used to calculate the inflow head graph from the rainfall head graph. What is rainfall head graph? So this is rainfall head graph. This one is the rainfall head graph. Means the temporal intensity. The temporal intensity of the rainfall. For example, from 0 to T1, the intensity is A1. Sorry, this is the area. So this is the contributing area. Not this one. Sorry. This is the head graph. Okay, this is the head graph. This is the head graph. Means the temporal change of the intensity of the rainfall of the design rainfall So the time area curve actually showing the relation between the travel time to the catchment outlet and the location within the catchment. So this method actually also does not consider the attenuation of the runoff hydrograph associated with the storage effects, similar with the rational method. Not consider the temporary storage effect in the basin, in the catchment. So also this method is also limited to small catchment area, Now for the rural catchment, so the isochrones, so the isochrones lines are used, okay, based on the travel time to the catchment outlet, based on the travel time to the catchment outlet. For example, this one we use the isochrones. This one we use the isochrones to divide the catchment into 5 sub-catchment, divide into sub-catchment, okay, A1, A2, A3, A4, A5, okay, because they have different travel time to the catchment outlet, okay. For example, A1 have the shortest travel time, A5 have the longest travel time to the catchment outlet. So for each sub area, so we need to calculate the area, the effective area, and also the time of concentration, and also the we need to calculate travel time from the drain inlet to the outlet of the entire catchment. So actually, this graph about time area histogram is the time area. It's called time area histogram. So this is the showing the contributing of the catchment with time, means the contributing area of the catchment, the temporal contribution of the catchment area. For example, from 0 to T1, the catchment A1 contributing, and this T1 to T2 is the contributing area is A2, okay, etc. So what we need to do is to use the time area histogram and the head graph. This is the head graph. So this is the rainfall head graph, okay, rainfall head graph. This one. So this one is the rainfall head graph. So with the rainfall head graph and also the time area histogram. So with these two graphs, we can get the using the time area methods, we can get the input head graph. So you can see that for the head graph, okay, for the head graph, actually it is a representation, a graphic representation of the relation between the rainfall intensity and time. So it means how the rainfall intensity change with the time. For example, from 0 to T1, the intensity is I1. From T1 to T2, the intensity I2. T2 to T3, the intensity is I3. Actually, it's a bar program. It's a bar diagram. Actually, it's a bar diagram. So the area under the head graph gives the total rainfall occurred in that period. I mean, the area. I mean, total area gives the rainfall. Total rainfall occurred in that period. So it's very useful actually to present the characteristic of storm, and it's particularly important in developing the design storm to predict the extreme floods. So the head graph can be developed based on the synthetic rainstorm profiles. Okay, just back to the synthetic. Okay, and also you say, remember there's one question from the students about whether the maximum is at time 0. Actually, it's not time 0 actually, because it's symmetrical. So you can see that normally the maximum is at the mid of the time period. Okay, it's at mid of time period. Okay. So because it is symmetrical, so we need to consider the both left side and both sides if we take the profile, to develop profile. So that means for 40 minutes rainfall, for 40 minutes rainfall, so we need to look after the profile from minus 20 minutes to 20 minutes. Okay, minus 20 to 20 minutes. We use the profile. We use the profile to design the rainstorm. Okay. The time area method. Here we introduce the time area method for the rural catchment. Okay. So actually, the incremental area contribute to runoff varies through the storm. Actually, we can use the time area histogram, to represent the area contribute to runoff. So applying the rainfall intensity, applying the rainfall head graph over time increment in the time area histogram, we can have the runoff at the end of the increment. So we can have the runoff. So we can have the runoff of each time intervals by using this method. Okay. Normally, to show the how the rainfall intensities the relation between the rainfall intensity and also the time area histogram. So we normally put the time axis of the rainfall head graph to the left side. Okay, the left side. Okay, means to the left. Okay, to the left. Normally we plot the time axis of the head graph to the left. Okay, to the left. Okay, so I1, I2, I3. Okay. So next I think we'll be show you how to get that, how to use the time area method. So actually this one, okay, now at the very beginnings, we have this time area histogram. Okay, we have the time area histogram put here. So, and also we have the rainfall head graph. So the rainfall head graph actually normally I just mentioned the time axis to the left, put to the left. Now at the start, okay, now at start time 0, actually no any rainfall on the catchment. Okay, no rainfall on the catchment yet. Okay, so no rainfall on the catchment, so that means there's no runoff. Okay, no runoff, so the Q is 0. J0 means Q is 0. Okay, let's move step by step. Can show very clearly actually shown very clearly the steps of the time area method, the steps of time area method. So in this, in the time ti, t1, sorry, the time t1, the time t1. So we can see that the contributing area is a1, means contributing area is a1, and also in the intensity, you can see that the intensity from the 0 to t1 is the I1, is I1. So we can easily to have the we can easily to have the runoff I1 times A1, I1 times A1. Okay, I1 times A1. Okay, have the runoff. Okay, so we have a runoff because at time T1 only the A1, only the area A1 contributing to the runoff. Okay, now let's move to the next time T2. For time T2, you can see that the contributing areas, there are two contributing areas, so A1 and A2, A1 and A2. But the intensity change, the intensity on the A1 change, the intensity on the A1 change to T2, I2, and also the intensity on the rainfall intensity of the A2 is I1, is I1. So now we have the runoff of the from the catchment outlet. Okay, it means the flow of at the catchment outlet is I2 times A1 plus I1 times A2. Okay, because only the two areas contributing to the runoff. So here you can see, you can plot on the hydrogram. So with outlet flow, and so we can plot this hydraulic here. Okay, hydraulic graph here. Okay. So next T3. Now, if for T3, you can see that the A1, A2, A3, the three areas contributing to the runoff, right? But you need to careful about the intensity, rainfall intensity on each subcatchment. The rainfall. Now we can see that the rainfall intensity on A1 is I3, on A2 is I2, on A3 is I1. So you be careful. Actually, this is this example showing very good method, to using the time area method. Okay, so you may not you are very clear. Okay, by using this method, you are very clear the contributing areas, and also you also need to, and also you can clearly know the intensity, the rainfall intensity on each area. Okay, on each area. Okay, it's very clear. So you can see very clear I1, A3, I2, A2, I3, A1, right? So you can very easily list this one. Means for time T3, so you can see that the runoff, the total runoff is this one. Means the three area contributing. At time T3 also, the three area contributing. So which three areas? A2, A3, A4. Means A1 here you can see not contributing to the runoff because there's no rainfall on A1, because the rainfall only, for example, 30 minutes. 30 minutes, okay, means after 30 minutes there will be no rainfall on the A1 because the rainfall will only the rainfall on the A2, A3, and A4. Okay. Because after the 30 minutes, actually the rainfall moved to the A2, A3, A4. Okay, that means no rain on the A1. So the A1 does not contribute to the runoff. Okay, so A4, so you can see the contributing area A2, A3, A4. So you can see the corresponding rainfall intensity here very clearly. Okay, I3, A2, I2, A3, I1, A4. Okay. So next one also, there are also three contributing area, A3, A4, A5. Okay. So you can see at the peak flow inflow is here at time 3. Sorry, at time 4. At time 4. So yes, the contributing area is the A3, A4, and A5 because there are no rainfall on A1 and A2. Okay, anymore, no rainfall on A1. Now at time 6, at time T6, you can see that the only 2 areas contributing, A4 and A5, A4 and A5. So you can see the corresponding intensity, I3 for A4, I2 for A5. Okay, only 2 areas contributing. So then move on for T7, for time T7. So only 1 area contributing, means last area, the A5. So the intensity is I3. So at T8, so at time T8, so you can see that the no area contribute to the runoff. Means the rain, there's no rain on the whole catchment. No any rainfall on the catchment. Means the rainfall may move to another catchment area. Okay, already moved to another catchment area because it's only a 30 minutes rainfall. Okay. Any questions you have? Any questions? Okay, great. Now for the time area method, I think this is a summary. For the urban catchment, they can be divided into sub-catchment. I just showing the case. The catchment can be divided into 5 sub-catchment. Okay, based on the effective contributing area. And also for each sub area, we need to know the effective impervious area, and also the time of concentration, and the travel time, and also travel time from the drain inlet to the outlet of the entire catchment. So we can plot the time area histogram, okay, and also we can get the rainfall headograph from the synthetic symmetrical rainfall profile from the manual, okay, and also apply the time area to get the inflow hydrograph to the storage basin. So this is that. So next, I'm going to show some examples, I think. Okay, show some examples. Okay, question 4 and question 5. Question 4 and question 5. Let me see. B. This is answers. Let me see the questions. Oh, I need to upload this ones. Workshop revision. Just wait a minute. Question 4 and question 5. I think you already download the revision material already, right? Revision questions 4 and 5. Let's look at the 4 and question 4 firstly. Let's look at the question 4 firstly. So question 4 actually, I think it's part C. The part C. Can you see that? The time area contribution curve for an urban catchment and the 15 minutes rainfall distribution given below. So here you can see the time contributing area. The total contributing area is 20 hectares. So be careful, this is the area, is hectares, okay? And also be careful, this is the total contributing area. So you need to convert to contributing area, okay? I'll show you later. And also this is the rainfall height graph, means the rainfall intensity at 5 minutes interval. Okay. So you need to estimate the runoff hydrograph or the input hydrograph produced from the catchment using the time area model. Okay. So actually this one is very you need to clear that. First you need to convert the you need to know the these are the contributing area, total contributing area. So that means the total area of the catchment is 20 hectares. 20 hectares. So that means from 0 to 5 minutes, the contributing area is 3. 5 to 10 is what? It's 5. Okay, it's 5. So 10 to 15 is 2. 15 to 20 is 10 hectares. So I can show you the solutions. So this is the estimated. So this is the estimated runoff hydrograph. Actually, as I mentioned on the first, you need to convert the total contributing area to the contributing area for each time intervals. Then you use the time area method to calculate. For example, from T0, of course, the runoff is 0. From the T time 5 minutes, so the contributing area is what? Is 3, right? Is 3. Yeah, the contributing area is 3 hectare. Okay, it's 3 hectare. It's 3 hectares. Okay, so and also the let me see the intensity. So the intensity is 5. Okay, the intensity is 5. Okay, it means 5 times 3, and of course you need to convert that to the unit. Convert the unit. This part used to convert the units. Okay. 5 times 3 means 5 is the intensity. 5 is the intensity, and the 3 is the contributing area. 3 is the contributing area. 3 hectares. And also conversions. So this part 1,000 and 10,000 and over 1,000 times 60 times 60. Actually, this is used to conversion the units. This is used to convert the units. So because the hectare is 10,000 square meter. Okay, the hectare. So one hectare. So 1 hectare is the 1 hectare is 10,000 square meter. Okay, square meter. And also we need to change it to the seconds. Change to the meter seconds. Because the intensity is what? Because the intensity is millimeter over 1 hour, right? Millimeter over 1 hour. So that means here we change the millimeter to 1 hour to the meter per second. Change to meter per second. So so this part, I just repeat that this part is to use to convert the units. Okay, is that clear? Okay, so for time 5 minutes, so the intensity is 5, so the contributing area is 3 hectare. So we can have this one, the runoff, total runoff to the outlet. And also for time 10, they're contributing 2 areas, 3 hectare and 5 hectare. And also the intensity is 10 and also 5. Okay, for the A1, the intensity is 10. For the A2, the intensity is 5. And also this part also used to convert the units. So then step by step, so you can find out the runoff hydrograph or the input hydrograph of this rainfall. Of course, you can plot this one in a rainfall input hydrograph. Okay, so you can plot a hydrograph here, hydrograph by using, for example, a graph paper. Okay, any questions about this? About these questions? Hello, any questions? Okay, now we have a break. Okay, back at 11:50. Okay. Have a short break. Okay, 10 minutes, and back at 11:50. Okay. Okay, after a short break, we continue this morning's workshop. Actually, next is about the question 5. Question 5. Let me see the question 5. So question 5 is also about the by using the rational method to calculate the here's the you can see here is the question 5. Question 5. Actually, this is also from a past exam paper. Actually, 53 hectares urban catchment has the following time area relationship. So that means the time from 0 to 50 minutes. So you can see the total contributing area. Here, you'll be careful. Here is the total contributing area. Okay, so that means you need to know the contributing area for each time intervals. Okay, for example, from the at 10 minutes, the contributing 0 to 10 is 10. So from the 10 to 20, the contributing area is what? Is 15. So from 20 to 30 is 7. Means contributing area here. I mean from 30 to 40 is 8. From 40 to 50 is 3. 3. So these are the contributing area for each time interval. So the head graph, the rainfall head graph is given here. 40 minutes storm, 40 minutes storm, 40 minutes storm from 0 to 198.42. From 10 to 20 minutes is 158.75. Symmetrical. You can see this is symmetrical because this is from the synthetic rainfall profile from the menu. Okay, so you can see they're symmetrical. So actually, similarly, we use the time area method. Okay, of course you can draw the time area. You can draw the time area histogram here. Okay, and also you can draw the rainfall headogram. You can draw the rainfall headogram here. Okay, you can draw the, and also you can move the rainfall head above the time area histogram step by step. Okay, step by step. So I would suggest you use this method. Use the method in the examples to move this to move the rainfall intensity, the head graph above. Okay, above the time area, histogram, step by step. So you clearly know, which area contributing to the runoff, and also the rainfall intensity on each area. Okay. Let me see the solutions. Now the solutions for these questions is here. Now, of course, first you need to get the contributing area. In these questions, the conversion factors of the unit is this one. So this one is the unit conversion factor. Okay. So the first at time 10 minutes, the contributing area is 10. 10 hectares. So, and also the intensity is this one. So for time 10 to 20 minutes, so the contributing area 10 and 15, 10 to 15, and also these are the corresponding area, corresponding rainfall intensity. For time 20 to 30, so the 3 area contributing to the runoff, to the total runoff. For time 40 minutes, so 1, 2, 3, 4 area contributing runoff. For time 50 minutes also 4 area contributing to. But for time 60 minutes only 3, and 70 minutes only 2, and 80 minutes only 1, and 90 minutes no area contributing to runoff. So you can see here are the runoff hydrograph of this rainfall. Okay, now let's move to the next one, the question 2D, the exam question 2D, exam question 2D. Now attempt these questions, okay? You can download that. I give you 10 minutes, okay? I give you 10 minutes. Let me see. Yes, this question, use time area to determine the to estimate the runoff hydrograph produced for the catchment using the time area model for the ARI of I think it's 100 years, and also the 50 minutes duration storm. So be careful. This question, the does not given. Okay, does not given. So the intensity does not given. So let me just think about how to get the intensity. How to get the intensity. Okay, I give you 10 minutes to think about these questions. Okay, attempt these questions. Hello. Yeah, give me some response. Okay, thank you. Okay, now 10 minutes. Okay. I said just mention that these questions you may need to think about how to convert this distribution to intensity height graph. Okay, anyone finish these questions? Please let me know. Or I'll give you a few more minutes. Hello? Okay, now I think 5 more minutes. Okay, 5 more minutes. Okay. And if anyone finish these questions, also please let me know. Okay. Okay, anyone finish? All right, 20 minutes, I think already. Still need more, a few more minutes? Okay, thanks. So this question, I just see the area is, I think the area is not, here is not correct. Yeah. Actually, this is 45, 45, it's 45. Okay, change that. So this is 45. Okay, let me see the. Actually, these questions, the problem is the difficult part is the intensity. Okay, the rainfall hydrograph is not given. It's not given. So we only know the ARI is for 100 years, and now the duration of the storm is 50 minutes. 50 minutes, and also the distribution of the rainfall given from 0 to 5, 5 to 10, and 10 to 15 minutes is given. Okay, so that means you need to convert the intensity. You need to convert the intensity to the sorry, to convert the rainfall to convert the rainfall to the intensity. Convert the rainfall, total rainfall to intensity. I will show you now. I'm going to show you how to do these questions. Okay. Okay, actually don't worry. I will upload the answers to the canvas after the workshop. Okay. Now let me see. Now for these questions, as we know that now you can see that I shared the slides already. Okay. Now, firstly, we don't know the intensity. We only know the distribution. 33% and 47% and 20% here. Okay. So how can we get the intensity? How can we get the rainfall intensity, and also how can we get the rainfall hydrograph? So we need to use the IDF table. So because these questions, the ARI is 100 years. Okay, 100 years. Okay, and also the rainfall time, the rainfall duration is 15 minutes. 15 minutes. So we can get the intensity here. Okay, this also based on the old version of the manual. Okay, so the intensity 215 millimeter per hour. So that means we can get the total rainfall here. We can get the total rainfall. Total rainfall, that means during the 15 minutes, the total rainfall, because we assume that during this 15 minutes, the uniform, the rainfall intensity uniform. So we convert this to the total rainfall during this 15 minutes. Okay, so 53.75 millimeter. Okay, so you can get the total rainfall 53.75 millimeter. Okay, now you're using the distribution. Now use the distribution, you can get the rainfall, the depth of the rainfall for each time intervals. For example, because this from 0 to 5 distribution only 33%, it means 33% times the total rainfall. You can get the rainfall during 0 to 5 minutes. And similarly, you can get the rainfall 5 minutes to 10 minutes, and also the rainfall from 10 minutes to 15 minutes. Okay, and then you convert that to what? To intensity. To intensity. How to convert? I mean, over time. Time is what? 5 minutes. 5 minutes. So is that clear? how to convert this to intensity? Any questions? Hello? Any questions to convert the rainfall intensity? No questions? Okay, now it's clear to you, I think. Okay, now next is the contributing area. And the contributing area actually from time 0 to 5 is 10 hectares. So we convert to square meter, means times 10,000. 5 to 10 minutes is 100 is 15 hectares. So 10 to 15 minutes is 20 hectares. Okay, so this is the corresponding intensity. So you will use the conversion factor here. Okay, so then you list them in a table. You list all the information in the table from time 0, time 5 minutes, 10 minutes, and until 30 minutes. Okay, now you use the time area method. Okay, so you can find out the contributing area. So time 5 minutes, only one area contributing. Time 10 minutes, 2 area. Time 15, 3 area. And time 20, 2 area contributing to the runoff. And the time 25, only 1. Time 30, there's no. So finally, you can get the runoff estimated runoff hydrograph of this question. So of course, if this question asks you to draw the runoff hydrograph, so actually you can draw like this now. Okay, so that means by using this runoff at each time interval you get from this table, so you can plot them in a graph paper, for example. So you can get this runoff hydrograph. So actually, this question actually is different with the question 4 and question 5 I just show you, because this the intensity, the rainfall intensity, not given directly, not given directly. So you need to use the IDF table to find out the intensity for the 15 minutes, and then use the distributions to get the rainfall for each time intervals, and then with the rainfall for each time intervals, you get the intensity for each time interval. Okay, so that is the difference. So that is the difference, I think. So actually, this question I say is an example. It is good examples for you to know how to convert that to the intensity. To convert that to the intensity rainfall intensity hydrograph. Okay, now I think this morning we stop here. Okay, so next this afternoon actually I think it's lunchtime, or so we have 1 hour lunch, 1 hour for the lunch. The afternoon we'll move on to the routine. Okay, to the routine. So how we now actually this morning we introduced the time area method, how to get the inflow hydrograph. Okay, remember they have two hydrographs. Okay, for the basin design. Okay, so next we'll learn how to get the outflow hydrograph by using the routing method. Routing method. Okay, now I think I conclude this morning's session here. Okay, and now so we continue this afternoon at 1:30. Okay, 1:30. So we have 1 hour for the lunch. Okay. Hello. Okay, great. And I'll see you this afternoon.